In this video, we'll show another example of using the ODE solvers in Matlab to solve initial value problems. And this time we'll compare the different solvers to show how the selection of the solver is important for some initial value problems. We're going to solve what's called the van der Pol oscillator. You may or may not have seen this equation before. It's a second-order, nonlinear, ordinary differential equation. And this equation has an interesting history. It was originally developed to describe some phenomena observed in electrical circuits, but has since been applied to fields as diverse as describing the action potential in neurons to describing phenomena in seismology, according to Wikipedia. To solve this using the ODE solvers in Matlab, we first need to write the equation in the state space form. Because this is a second-order ODE, we of course are going to need two initial conditions to solve it. We'll probably have an initial condition for y and another initial condition for dy dt. So those will be our state variables, y and y dot. Then we write the defining equations for the initial value problem for the two state variables. Of course, the time derivative of y, or u1 dot, is just equal to y dot, or u2. And the time derivative for y dot, or u2 dot, is the second derivative of y with respect to time, which we can find by solving the van der Pol oscillator equation for d squared y dt squared, by moving these terms over to the right-hand side of the equal sign. Remember that when we write the state space form, these equations should not contain y, they should only contain the state variables u1 and u2. Now that we have it in state space form, we're ready to convert it into Matlab. We have a script here that's formatted according to the template that I showed you before. We've transcribed some information about the van der Pol equation to the comments at the beginning. We'll start with initial condition of y equal to 2 and dy dt equal to 0. For the options, this time we'll use the optimset command, which builds the option structure using default values that Matlab will choose for us. This script is designed to compare solutions to different versions of the van der Pol oscillator using different values of the parameter mu. We'll use 4 different values: mu equals 1, 10, 100, and 300. And we'll solve the van der Pol oscillator using 3 different ODE solvers. ODE 23 and ODE 45 are both adaptive step size RKF methods. We'll also use ODE 15S, which is a predictor corrector implicit method that's optimized for solving stiff problems. The function calls for the ODE solvers are built into a for loop that iterates 4 times. That way we can select mu from among the 4 candidate values 1, 10, 100, and 300. When using different values of mu, we also need to use different values of Tmax so that we can see the same number of oscillations in the van der Pol oscillator. So Tmax is also selected inside the for loop. This script is designed to build a table that shows us how many steps were required to find the solution using each of the 3 ODE solvers for each of the 4 cases represented by different values of mu. The method will also produce 4 plots that show us the solutions from ODE 23 and ODE 15S for each of these 4 cases. Notice as we're running the program here that the 4th case is taking a long time to compute. Okay, now we're done. And we've got our 4 plots here. Each plot shows at least 1 full cycles of the van der Pol oscillator for mu equals 1, 10, 100, and 400. When mu is equal to 1, ODE 23 needed 85 steps. ODE 45 and ODE 23 used different Runge-Kutta algorithms. ODE 45 required 129 steps, and ODE 15S required 110 steps. So the solutions are comparable. When we increase mu, we're making the problem more stiff. This makes it difficult for ODE 45 to converge using larger step sizes. ODE 45 requires more than twice the number of steps compared to ODE 23 and ODE 15S. If we make the problem even more stiff by setting mu equal to 100, we now require 22,000 steps or 67,000 steps for ODE 23 and ODE 45. However, ODE 15S has only a marginal increase in the number of steps required. When the problem is very stiff, for mu equal to 300, ODE 23 and ODE 45 require hundreds of thousands of steps. In fact, ODE 45 requires more than 1,000 times the number of steps as ODE 15S. This is why it took a long time to compute the solution using mu equals 300. Clearly, this problem is stiff, and ODE 15S works far better. We can also see that difference when we compare the plots of the solutions. The solutions using ODE 23 are shown with the blue X's, and the solutions using ODE 15S are shown with the orange circles, drawn on top of the blue X's. Notice when the solution is changing more slowly, ODE 15S really spreads out the data. And when the solution is changing quickly, ODE 15S uses much more densely packed data points. But ODE 23 is unable to space out the data points, and that's why it requires so many more data points to solve when the problem is stiff. You'll want to be aware of this when formulating solutions, particularly to nonlinear differential equations and to stiff equations. You may think that ODE 45 is the best one to use. It uses a higher order Runge-Kutta method. However, ODE 45 requires far more function evaluations at each step than ODE 23, and it also requires an exorbitant number of steps in order to compute the solution. And this from a simple nonlinear system containing only 2 equations and 1 parameter. For more complicated systems that have multiple equations and multiple parameters, it may not always be immediately apparent whether the problem is going to be stiff or not. With experience, you can learn to identify features of ODEs that might predict this kind of behavior that will help you to select which ODE solvers to use.